Hi, welcome to video 9.10, C, approximating function values using power series, which we just pretty well started anyways. So this is from the worksheet number 30. Use series to evaluate accurate to 3 decimal places the definite integral 0 to 1 root x e to the negative x squared. So we're going to start with our power series for e to the x. Here's the first 4 terms. Here's the summation notation. We're going to replace x by x negative x squared to get e to the negative x squared. Then we're going to multiply by x to the half because that's the square root of x, which is x to the half. That's a monomial. So when I multiply each of those terms by x to the half, I'll get the following. And now I'm going to integrate. So remember the way we integrate, we're actually integrating square root of t e to the negative t squared dt from 0 to x. But we can just look at it as we're integrating. So we're integrating x to the half. We get x to the 3 halves over 3 halves, etc., etc. And we're going to be evaluating that from 0 to 1. Now, because it's a polynomial with no constant term, the 0 means they'll all be zeros. When we replace all of those x's by 1s, we get 2/3 minus 2/7, etc. Now, you are going to have to, I'm just kind of stopping here, but they want it to correct to 3 decimal places, which means you're going to list the terms until you get to the first term that's less than 0.305. So it turns out that the 7th term, by the way, is the first one that's less than 0.0005. So you'll use the first 6 terms. Okay, and when you do use the first 6 terms, you'll get this, round each term to 4 decimal places, and then round the final answer to 3 decimal places. Okay, this is in the textbook, page 688. Use a power series to approximate the value of the integral with an error of less than 0.0001, i.e. find the first 4 or 5 terms of the series of the integrand function, then integrate those first few terms, and then for each term, plug in the 2 limits of integration and subtract, and write out those terms until you hit the first term that's less than 0.0001. Ignore that term and all the others to the right, and just keep the ones to the left. So for number 68, let me pause and pull up the text. Okay, so we're looking at number 68 in the textbook. So here's number 68 right here. It says use a power series to evaluate the value of the integral with an error of less than 0.0001. So here's our function, and we're going from 0 to 1/4. So for ln of x plus 1, what we're going to do is start with our 1 over 1 minus x, which is our geometric series. And then we're going to replace our x by negative x. So replacing x by negative x, all the odd ones will have a negative. Then we're going to integrate that, because when we integrate 1 over 1 plus x, that's when we get the ln of 1 plus x. So when we integrate that, we're going to integrate 1, we'll get x, we'll integrate x, we'll get x squared over 2, etc. And now we need to multiply by x, so we'll multiply by x, which is just a distributive, which will give us this series right here. And now we're going to integrate that. So when we integrate it, we're going to get, as we integrate each term, the integral of x squared is x cubed over 3, etc., 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 evaluated from 0 to 1/4. When you plug in the zeros, these will all become zeros, so it really just comes down to plugging in the 1/4. I don't know why I wrote all these zeros. So 1/4 cubed over 3 minus 1/4 to the 4th over 8, etc. And that will give these decimals right here. And as it turns out, the third one is already less than 0.0001. So we actually are only going to use the first 2 terms to get a good approximation of 0.00473. Again, because they're saying they want an error of less than that, I'm assuming they want an answer of 5 decimal places. So I rounded these. Well, actually, I should have rounded them to 6. And by the way, you could not integrate this. Good luck with that. You can't do that. Okay, number 76. Use a power series to approximate by hand the area of the region bounded by y equals cosine root x, the x-axis, and the lines x equals 0.5 and x equals 1. Use the TI to verify. And by the way, they forgot to tell you, but they want an answer of less than 0.0001. So y equals cosine x, of course, cosine root x, you don't really need to know what the graph looks like, which is why I have these question marks, but you do know that between 0 and 1, the cosine of 0 is 1, and 1 radian is still in the first quadrant, so the cosine is going to be between 1 and 0, so it will be positive. Okay, so we're going to start with our power series for cosine x, which you should know. Remember, it's an even function. Then we're going to replace x by root x. So root x squared, root x to the fourth, root x to the sixth. Then we're going to integrate term by term. And when we do that, we'll get x minus x squared over 2, and the 1 over 2 factorial is still there, etc., etc. We're evaluating that from 0.5 to 1. Now, there's no 0 this time. So notice how I'm doing this. I'm actually doing it term by term. So I'm taking the x, plugging in the 1, subtracting, and plugging in the 0.5. And then I'm going from there. Okay? And then minus, and then I take this term from 0.5 to 1. And then plus, and then I take this term from 0.5 to 1, because you can't do all of them because you don't know how many to do. Turns out that the fifth term, which is 1 over 2,000, this one right here, 5 times 8 factorial, and when I go from 0.5 to 1, I'll have 1 to the fifth minus 0.5 to the fifth. Turns out that that is less than 0.001. So I'm not going to use the fifth term. I'm going to use the first 4 terms. And when I use the first 4 terms, and actually evaluate that, I will end up with 0.3243. Did not mean to do that. Okay, back to the worksheet. Number 18, find the first 3 non-zero of the Taylor series for cotan x at pi over 2. Okay, so using the table method, if you haven't memorized the formula for tan x, would be helpful if you did, but in case you didn't. So you will get this. And, oh, I'm sorry. No, forget it, because this is at pi over 2. So you would have to actually make the table. I'm not going to make the table, but if you made the table and you did it at pi over 2, you would get the following, which simplifies to this. Now, this is a tricky one. Remember cofunctions. The cotan is the same as the tan of 90 minus x, or pi over 2 minus x if you're in radians. So I have tan of x. I can replace x by pi over 2 minus x. So take all these x's and replace them by pi over 2 minus x. And then once I've got, which is basically cotan, and then I have my answer right here. Now, they're writing it in the more traditional x minus a, so they're just basically factoring out the negative here, is all they're doing. And number 20, use the answer in number 18. So we have to have number 18, which is this answer right here, okay, for cotan x. And term by term differentiation to find the first 3 non-zero terms of the Taylor series for cosecant squared x at pi over 2. So this is what we got in number 18. What we're going to do is multiply by -1, because remember the integral of negative cotan will give positive cosecant squared. So I simply multiply by -1, which all that does is change these signs on the outside. And then I'm going to take that and integrate it, because the integral of negative cotan x dx is cosecant squared x. So I integrate this, I get 1. Then I get, what is happening? Let me pause for a second. Okay, I'm back. We're not integrating, we're differentiating. So when you differentiate x, you get 1 minus 0 here, then you get plus 1/3 times 3, so 3 times a third, which is 1, times x minus pi over 2 to the 2 times 1, etc. And that's what you'll get. Number 22 also asked you to take the answer from number 18 and then use term by term integration to find the first 3 non-zero terms of the Taylor series for ln of sine x. So we start with our answer from number 18, and we're going to integrate, which they actually tell you to do. And when they get complicated, they will tell you what to do. So we're going to integrate cotan x, and the integral of cotan x is ln absolute value sine x. So that's what happens. So ln sine, we're going to integrate the cotan. So we're going to integrate cotan x. When we integrate this, we're going to have negative x minus pi over 2 to the 2 over 2 minus 1/3 x minus pi over 2 to the 4th over 4. So that's where the 1/12 comes from. So one more time, know these series. These are the ones you want to know without having to make the table. 1 over 1 minus x, e to the x, sine x, cosine x, remember odd function, even function. And to get from one series to a next, you have options of substitution, multiply or divide by a constant or monomial, differentiate term by term, integrate term by term, add or subtract two series.